Hello, good day. My name is Kenneth Verheggen. Thank you for visiting our introduction video to our grid engine called Pladipus. Pladipus was developed by me at the Compomics group at Ghent University, which is part of VIB. So technical advances have definitely led to more complex and bigger science. For example, this is what a mass spectrometer looked like back in 1969. So when we open a time portal and fast forward to today, then you see that this entire wall was actually replaced by this machine, and this machine is spewing out data in sizes that were not even imaginable nearly 60 years ago on a daily basis. And this evolution is not stopping. It is also reflected in the data sizes for public repositories, where the total amount of spectra posted in complete submission is rising ever so. So as you can see, the data gets bigger and bigger, and this is only the complete submissions, I have to say. So the partial ones are not even taken into consideration, nor are the private projects. So yeah, science is becoming more complex, and this also has benefits. Each dataset brings added information, and that allows us to move from a detail-centric view to a system-wide field. In other words, we get to see relationships between things in the datasets, for example, protein interactions and things like that, and pathways. But it also comes at a cost. Since these datasets are enormous and growing so far, maybe have become too much to handle on a single computer. And there are options to process, mine, and understand this data. For example, supercomputing. It's up for the job, but it's not very scalable because the hardware is highly specialized and customized, so it's not easy to plug more processors in, for example. The housing is also not that cheap. If you think about cooling, power, maintenance, the cost of the building, and those are just the first things that come to my mind. Also, the lifetime is quite limited. The powerhouse will someday come crashing down and need replacement. It's everything or nothing pretty much with the supercomputers. And the initial cost is around 4.5 million euros. This is the number I got from the supercomputer at Ghent during its inauguration, the Tier 1 supercomputer. So yeah, why don't we go towards a cheaper alternative and use existing hardware in the form of a grid computing network? It's immensely scalable. I mean, you can plug whatever you want in there as long as it has a network connection and can actually connect to the other nodes. It's fine. And the price will be that of commodity hardware. If you want to expand, you need to just pay for a regular desktop computer instead of millions of euros. Sorry. The lifetime is unlimited. This is a tricky one to say, but what's meant with this one is that it's like an organic organism. You can replace your machines as you go, just like you would do with cells in your body. As you age, you get to replace your cells. And it can be used for more than just heavy computing. Every desktop can just be used by a client using a word processor or whatever else they need for their tasks. So maybe allow me to explain you what grid computing is. It is basically a supercomputer, but built like a biological system. And it all starts with one controller that's connected to another computer. And they delegate jobs across a network of similar computers. Now, why would we stop here and only include new expensive hardware? We can also go to the lab. When someone's not using this PCR machine, we can use this computer since it's just idling over there. It has a lot of compute power, but it's not using it. Or even the library. We can go to the library at night, for example, when all these machines are there, they're paid for, their housing is paid for, the network is paid for. So basically we can just use them to do computations. And in the ultimate case, we could just even hook everything onto the World Wide Web. So we can create a grid that potentially exceeds all supercomputers combined. Now, this is a concept that already has been successfully applied. For example, Galaxy and Galaxy P provide a large amount of tools, but they're not that trivial to customize, and the setup can be quite cumbersome, even though there are very good tutorials out there, and I definitely recommend having a look at Galaxy P as well. Especially if you want purely cloud-based solutions, which can also be quite expensive compared to the grid where we use existing hardware. Then there's another project, or rather the folded project and its predecessor, the Rosetta at Home project, that specializes in using idle computers, but that's again a tricky thing because it's so specialized they basically only use it for protein folding. That's why we created Pladipus, to create the versatility that Galaxy P offers in providing as many tools as we can, and it's virtually unlimited. Everything that has a command line can technically be run on the framework with full this efficiency of using idle computers. So you get a cheap but very powerful network that can do calculations whenever you want, combining these benefits. This is an example benchmarking of the use of Pladipus, and show that it works. I mean, on the y-axis you see the wall time, which is the total processing time required to perform sequence database searches on the 52 CPTAC files that were included in the search, followed by the post-processing by peptide shaker. What the pipeline actually consists of is not that important. What is important is that this graph shows that by adding more nodes to the network, or by increasing the network size, you get a decrease in the wall time as expected. Now, before going any further, there are some minor requirements, but you get a lot of benefits out of it. So on your network machines, or the machines that you want to implement Pladipus on, you need to have Java 8 installed. You're also going to need a machine running an active MQ server, which will distribute the tasks across the network, a machine running the MySQL server, which will keep track of the running tasks and the running jobs, and give powerful feedback to the user to know what's going on. These can of course be run on the same instance. It's pretty versatile. You need a network connection, which is again pretty standard because otherwise machines can't communicate with each other, and a place where the data can be retrieved from and posted to. Retrieve from can be as simple as a URL or a local file, but posted to implies that you need a shared storage space somewhere, so where all workers can post their results. It's not exactly a must, but in most cases this will be a very valuable asset. You also need the machines to host a Pladipus executor, which is the section that will perform the task and is expanded nearly limitlessly. And also you need one good ID, because as I mentioned before, you can run anything you want on Pladipus. The examples we give are just standard use cases, but it's very easy to implement your own algorithms. Okay, so how does the Pladipus system work? I think it's a good section here to explain that before showing the demonstration. So basically you need two files. You need a file with job parameters, and you need a file that contains a run template. This is an XML file, this is a TSV file, but more details will follow on that. And what happens is Pladipus takes your template run and fills it with the parameters you provide, kind of like what's happening here in this injection mold. So you mold it into a job, and the job gets pushed onto the network of computers, and one of these will get it and execute it, while the other ones pull sequentially from the queue. So basically you can push whatever you want on there and just leave for the weekend, and your network will take care of it without intervention. So as I said earlier, the run template is a mold for the jobs, and it's an XML file that looks like this. Now this might look a little bit intimidating at first, but there is a very nice graphical user interface that allows you to set this up and get this XML file generated for you. So this is just an example to show what it looks like on the inside. And then this is a more important one because you will actually have to make this one yourself, is the job configuration file to fill the template with the parameters. Well, you don't have to make it yourself. If you make a template using the graphical user interface, you will get an empty file like this. And every column represents a parameter that was specified in a template. For example, these are run parameters, so these will be the same for every run, but these are job specific parameters, and these are the ones that you will find in your column. So there's input parameter file and assay, for example. These are the headers of your columns. That's pretty much all there is to it for now. With that, I would like to invite you to the brief demonstration in the next video. Pladipus, the manual and the examples are available at our GitHub. Thank you for watching, and should any questions arise, please do not hesitate to contact me at kenneth.verheggen@ugent.be.